In this videotape lecture, we're going to be talking about event programming, which is a new type of programming that most likely you have very little experience with. The best place to look for a few notes on this topic is Scott, section 8.7. Unfortunately, there's not really a good textual document that I could find that has something about event programming. So this videotape lecture is really going to be your next best source of information about event programming. So thus far in your computer science career, you've probably or should have had experience with what's called imperative programming and with object-oriented or OO programming. And event programming is a third kind of programming where the program is driven by events. And to give you three examples, we're going to talk about graphical user interfaces, which we'll refer to as GUIs, simulation, and animation. So each of these three types of applications is event-driven. With a graphical user interface, what you have are things like mouse events, keyboard events, and then higher level events like if you enter something into a text box, you might have something called a text change event, or if you push a radio button, you might have a button event. So these are all events that when they occur, the user interface has to happen in some fashion or respond in some fashion. So for example, here in this notebook application, if I'm to go and click on File, that's a mouse event that gets translated into something that drops down a menu. Then if I go to, say, the New button, that creates a menu action event, and as you can see, it caused a new window to be popped up with a new notebook object. So that's the first example. Simulation is the second example. Let's say that I want to simulate operations in a bank. So I have customers that come into my bank, and I have tellers that process them. So I have two basic types of people. I have customers and I have tellers. And I have two kinds of events. I have an arrival event, which indicates that a customer is coming through the door. So if I measure time from time 0, perhaps at time 5, if we're just measuring, let's say, in seconds, maybe there's an arrival event, and maybe I say that it's customer, so maybe that's time, then maybe the customer ID is 1. So I'd have arrival events that are occurring periodically, and then presumably I would have, say, teller events, where a teller gets a customer and processes it. So maybe the teller ID might be, say, 1, customer ID 1. And then I might have a time that it takes to complete. So time to complete, maybe it takes 120 seconds. So basically, my simulation would consist of generating a series of arrival events for customers periodically coming into the bank, and then teller events where customers get matched up with tellers. So, and I would probably keep some kind of queue where the customers were placed into a queue if they had to wait for a teller. Okay, and as each teller became free, I could move a customer off the queue and have them be serviced by a teller. So that's the second kind of event-driven application. The third kind is animations. And for that, I have a picture of a game. And here you can see we've got a series of trains that are coming in. And in fact, we also can click on these little turnstiles in order to direct the trains into the different parts of the train stations. And you can see that each of them is controlled in some sense independently, and I might want some of them to go faster, some of them to go slower. You see that as they get near the station right here, it creates a little puff to indicate that it's going in. If it's not right, it creates an X. So there's all kinds of different events going on. Some of them are motion events where I'm moving the trains. Some of them are indicating success by puffing out some smoke. Some of them are using an X to indicate that I did not succeed in directing the train to the right station. So that's a third kind of program that uses events. So there's several characteristics to event programming, but the big characteristics is, one, they're event-driven. So the program is reacting to events. Each time event is processed, some action is taken to update state. So basically, you can think of the application as some state information. And each event, in some sense, is going to update that state information. So, for example, in the simulation of the bank, having a customer arrive causes us to check to see if there's a teller available. If there is, we create a teller event. If not, we assign the customer to a waiting queue. In the animation example, if we get an event such as a train move event, then we would move the appropriate train some number of pixels in our animation. So that's the first thing. We're event-driven. The second thing is that most event-driven applications have something called an event queue. So all events, as they come in, are placed into a queue. Now, some of them are what are called FIFO queues, for first in, first out. And an example of that would be many GUIs where the mouse events and keyboard events are processed in the order that they're received. But you could also have priority queues, and those would be more common in simulations and animations. In the simulation, the priority queue would probably be based on time of arrival and also when customers get out of the bank. So those teller events, one thing that they're probably going to actually be processed when the customer's leaving the bank. So if a customer is assigned to a teller at time, say, 180 seconds, and the event is going to be 105 seconds long, then we'd actually probably schedule the teller event for 295 seconds so that as the customer departed, we could collect some statistics. So the arrival and teller events would be prioritized by the time at which they occur. And similarly, in the animation example, the events are placed into the priority queue based on the time at which they need to occur. We always then remove the event which is closest to us in time. And again, there's a difference with a simulation like the bank teller. We just immediately remove events, process it, and then move on to the next one. Whereas in the animation, we actually have to wait until that time because we're dealing with a real-time application. Whereas in the case of a bank, we're simulating a application and we can go as fast or as slow as we need to. So these are the two strong characteristics of event programming. They're event-driven, and the control is in an event queue, and there's essentially a main loop that is simply removing events from the event queue, executing the events, updating the state information, and if there's some what we call presentation component, i.e. a graphical interface, then that graphical interface would get updated in response to changes to the state information. So compared to traditional imperative programming, there's a number of differences between event-driven programming and imperative. So differences between event-driven programs and imperative programs. The first difference concerns external versus internal control. With an event-driven program, the control is external. So in a GUI, it is the user who controls what happens. The user is the one who may press a key, select some menu, and the program needs to react to whatever the user has done. And in general, in an event-driven program, the program is reacting to events, and those events can arrive in any order. The program has to be ready to handle any kind of event at any time and do the right kind of processing. In contrast, with imperative programming, the control is internal. The program itself controls where it goes next, and it controls when it asks for input from the user, and it controls when it gives output to the user. That's not true with event-driven programs. With event-driven programs, it's the event that's in control, and you have to be able to respond quickly to events and typically update the state information quickly and then get some kind of visual representation of the update presented to the user. The second big difference is that event-driven programs have what's called distributed control versus the centralized control that you get in an imperative program. So in an imperative program, there's always one control point in the program, and you're basically you call a function next, you return from a function, you return to main. There's always one locus of control. That's not true in an event-driven program. Their control is distributed because at any given time you may have to respond to one of several types of events, like a mouse event, a keyboard event, or in the case of the animation you had a train move event, or an emit smokes event, or a create X event to indicate the train was into the wrong train barn. So at any time you have to be prepared to deal with different types of events. Each event will be handled by a different function. So we say control is distributed because you cannot predict in advance which function is going to get called next. Whereas in an imperative program, you're pretty confident about what function is going to get called next. The third difference is that with event-driven programs, you basically have a collection of independent cooperating processes. So I'm going to write independent cooperating processes. Whereas with imperative programs, you have a centralized control. So imperative, you have, again, centralized control. And I guess this does kind of repeat point 2 about distributed versus central, but basically with distributed, it's a loosely cooperating set of processes. With imperative, there's kind of a sense of always one piece of the code in control at a time while the others wait for them to be called. Okay, so those are the big differences. In this course, what we're going to be talking about is graphical user interfaces. It's kind of a very intuitive way to talk about events. we may consider animated programs when we get to concurrent programming, because often animations are implemented using threads. We're not really going to talk about simulations in this course. So the specific type of interfaces that we're going to be talking about in this course are direct manipulation interfaces. And direct manipulation interfaces are interfaces that display concrete objects that can be manipulated by the user and that represent application state. So display concrete objects that represent application state and can be manipulated by a user. So the classic example of the direct manipulation interface is the desktop. So with a desktop, you have folders. So here I have folders BVZ, I have applications. If I go to BVZ, I have a series of folders. So the folders are kind of representing the concept of folders of information on a desk. By clicking on them, I'm able to manipulate information. I can move information around. I can move files to different folders, basically simulating a desktop. Okay? This example with the trains was a direct manipulation interface. The objects are trains and train stations and tracks and switches, like you see me switching here or switching here. So you have also the time that remaining up here, the number of correct, which you see up here. So you have a pictorial representation of the state of the interface. So direct manipulation interfaces are particularly good for novices and intermediate users. Novices and intermediate users. And why would they be good for these two types of users? The reason is that these two types of users make use of what's called recognition memory. So recognition memory allows us to So recognition memory allows us to recognize objects when we're presented with them. For example, I might not know how to delete an object from this interface, but if I mouse around to the various menus, I might happen upon the fact that there's this cut option in the edit menu, and I recognize the fact that cut is a delete command, or that paste is a way to paste something into my document. Okay? By contrast, expert users like text-oriented interfaces. That's why a lot of experts like to use command line oriented shells for doing their programming. And also a good direct manipulation interface will provide shortcuts for experts to use, like here with the drop down menu you see that paste is the flower V, cut is a flower X, clear page flower K. So experts who remember the commands can quickly interact with this interface using the keyboard. So experts prefer text-oriented interfaces. That make use of recall memory. So recall memory is the ability to actually recall some piece of memory without being prompted. So for example, now if I wanted to cut, I could remember the flower X button without having to actually look through the menus in order to find it. So we're going to be talking about direct manipulation interfaces, and this was basically a brief introduction to the psychology of them. And moving on, with direct manipulation interfaces, they're basically divided into two parts. They have what's called a presentation component and a behavior component. So the presentation component is a pictorial interface that displays the application state. The behavior component is the behavior that the application displays in response to user input. So behavior that application displays in response to user input. And the user input is going to be in the form of events. So some event comes in, we call a procedure to update the application state. In response to this update to the application state, we update the pictorial interface, and then that cycle repeats with the user performing some other task, which is done via an event. Again, we respond via some function, update the application state, which updates the pictorial interface. So let's drill a little deeper into the presentation component and into the behavior component. So the presentation component is going to consist typically of two types of objects. One are called widgets, and one are called custom graphics. So widgets are predefined pieces of graphics, such as text boxes, menus, sliders, that allow the user to interact with an application. So predefined pieces of graphics, which we call the look, and behavior, which we call the feel, hence look and feel, that allow the user to interact with the application. And examples include things like menus, text boxes, radio buttons, or just buttons in general, checkboxes, radio buttons, sliders. These are all predefined pieces of graphics and behaviors provided by generic libraries. Java has it, Windows has a library, X has a library that provides these sets of predefined graphics. And these work well for providing input. If you look here, menus, text boxes, buttons, sliders, all are excellent at providing input. And in some cases, they're pretty good at providing output, like a slider may allow you to see a temperature, or a text box might display some information. But in general, widgets are better for input. And for output, it's basically better to use custom graphics. And custom graphics are graphics that are typically composed from primitive types like rectangles, lines, bitmaps, and text. So graphics composed from primitive objects and these objects are typically application dependent because they're going to be hard to duplicate across multiple applications. So for example, a chessboard has a certain set of pieces that aren't going to work on a checkerboard and are not going to work in some kind of fantasy board game. Or if I have a drawing editor, then I have an entirely different set of objects that I'm drawing than if I'm in a circuit editor and drawing circuits. So custom graphics are application dependent. We say that widgets, by contrast, are application independent because you typically can use them across different types of applications. So typically the input is pretty been standardized in modern graphical user interfaces, but there's no way to customize the custom graphics. And as a result, custom graphics typically take 1 to 2 orders more magnitude of programming effort because each one is different for each application. So 1 to 2 orders of magnitude more work than widgets, because with widgets you're simply typically creating some instances of them and perhaps setting some properties like a label or whether you're allowed to have one selection or multiple selections with them. Okay? And then with the behavior component, we've already talked about how the behavior component is controlled by events. Events can be things like keyboard, mice, pen, trackballs, data gloves, gestures. Now typically what happens is that most computers only support a limited number of events, such as mouse and keyboard events. And if you want to hook up a new type of device, then you insert a device driver. That device driver will tell the operating system how to translate the events for that device into events that the operating system understands. So as events get generated by the operating system, so we have the operating system and it basically gets input and it generates events. So it gets input from a mouse or a keyboard, it generates an event which it hands off to a window manager. Window manager is responsible for directing events to an appropriate window. And typically, the window manager actually has some of its own decorations that it's going to give priority to. So you can see that on here, some of the decorations are for this red one. It would cause the red button would cause the window to disappear. This yellow one would iconify the window, and this green one would make it fit the entire window. So window managers often put little decorations around the window that have top priority for events. But if the event isn't directed to one of those objects, it's then typically given to an application, and the application is then responsible for handling the event. So the window manager then passes the event to an application, which is responsible for handling it. Now, if the event is directed toward a widget, that's easy. Typically, the widget has predefined event handlers. If it's directed at a custom graphic, then that's an event handler that the programmer themselves will have to write. And typically, the programmer writes what's called a callback procedure. So the callback procedure is simply a procedure that handles whatever input we receive. So for example, if I have a rectangle and I have an event that causes me to want to move the rectangle, say to there, the callback procedure would presumably change the left and top coordinates of the rectangle and then cause it to be redrawn. And we often talk about two types of feedback that need to be provided by the behavior component in response to some event. One is syntactic feedback and one is semantic feedback. So two types of feedback that are getting provided. So syntactic feedback is feedback that is provided while an operation is ongoing, whereas semantic feedback is feedback provided when the operation completes. So provided during an operation and provided when the operation completes. The semantic feedback typically reflects some change to the actual application. So typically, if I was moving this rectangle right here, the syntactic feedback would actually consist of a dotted rectangle moving. That would give me an idea of where the rectangle would be placed if I were to release the mouse at that moment. Whereas when I actually released the mouse and completed the operation, the final semantic operation or feedback would involve moving the rectangle to its new location. Or you can see here, if I am going to perform some operation, let's say I wanted to print this. First of all, syntactic feedback here is the inverted blue or the blue rectangle that's appearing. Notice as I click it, it's going to flash for a moment, indicating that's the item I selected. And then the semantic feedback in this case is the dialog box that's going to allow me to select things. And you can see here that final or semantic feedback for a checkbox is a check. You can see that perhaps as I select this one, it grays a little bit. That's the syntactic feedback. The final feedback is the checkbox. The basic idea behind any operation is that as we're doing an operation, we have to provide some feedback that lets the user know that we are listening to the user and also gives the user some idea of what might happen if we were to release the or to stop the operation at that point. The semantic feedback actually shows the user how the application state information has been updated in response to this operation. In another lecture, we're going to talk about something called the Model View Controller, which is going to give us a principled way to create graphical user interfaces. We'll see that views will be the presentation component, and the controllers combined with the model will represent the behavioral component of the interface.